Hello everyone, my name is Igor Opaniuk. I work for Texas Instruments and currently I'm SNE in Security Working Group in Linaro. So today I'm going to present some current status of integration of Android verified boot support into U-boot. So basically we have two major parts of our presentation. First one, I will introduce some highlights about what is Android verified boot, what is currently done in U-boot, and what capability we've introduced. And second major part is going to be a discussion about leverage of trusted execution environment and how actually and what role it plays in Android verified boot. Android verified boot, so actually it's Google stuff, you can say that, that introduces new way of verification of partitions, so it establishes chain of trust from bootloader to system image. It provides support for integrity checking of Linux kernel RAM disk. It's also basically it's Android image, which includes Linux kernel RAM disk. Also, we have support of verifying root hash of DM Verity hash trees if this feature is enabled in Linux kernel. Also, second major feature is rollback protection. So basically, we provide some way of securing rollbacks and flashing old firmwares. And out of scope in this case, it's integrity of bootloader itself. So in this case, it should be vendor specific, so different vendors provide their own chain of trust up to bootloader. So in this case, U-boot to verify U-boot image or SPL. So everything is built around VB meta structure. VB meta structure contains crypto descriptors like hashes, hash metadata, public keys, and so on. And basically, it's kind of storage for all these descriptors for implementation of chain of trust and verification other partitions. First of all, what should be mentioned is that VB meta structure is versioned. It could be a separate partition, so we can flash into separate partition, and we can also integrate into boot partition. So it's already supported out of the box in libabb. And also maximum image size is 64K. So basically, it contains some header, fixed size header, 256 bytes. So some authentication data actually contains all crypto descriptors for verifications, this VB meta partition itself, and some auxiliary data. So it contains other descriptors to verificate other partitions. Android open source project provides two libs, two libraries, which has all capabilities for crypto capabilities and implements this chain of trust called Android verified boot. So they are provided under MIT and BSD 3 closed licenses. And the main idea of integration of these two libraries is that we need to use some C99 compliant compiler. We have to implement some, provide some basic runtime. It's at least types and implement also some layer, also runtime for such functions like memcopy, memset, malloc-free. And the second part of integration of these two libraries is some layer for block device layer, which actually helps to read some block data and further verifies the block data. So actually we introduce 4 callbacks which are used for working with partitions, different partitions. It's some per byte input output. It's read from partition and write to partition. Also a call for verifying VB meta partition itself. For validating VB meta publicly in case if we are storing some temper evidence storage, or it's, for example, integrated into U-boot binary. And also a specific call for receiving unique ID for partition. Also, we have to implement 3 additional calls, and currently it's under development. Why? Because we're going to leverage a trusted execution environment for working with rollback indexes and storing device log state. So in this case, about these specific 3 calls, I'm going to describe what particular we're going to do in the next couple of slides. There was a big discussion about how it should be invoked. So the first, as U-boot, basically how the process of loading of Linux kernel looks like. So basically we have 2 different steps. We have some eMMC layer, for example. We use eMMC commands to boot something to RAM, and then we use boot and command which basically consumes what was loaded into RAM and boots Linux kernel. So basically it consumes Linux kernel, it consumes some RAM disk, it consumes device tree blocks. And as we provide some layer for direct working with eMMC, so the eMMC subsystem, I thought it was not a good idea to introduce invoking of ABB from bootcamp. So basically, the better solution was to introduce some U-boot shell commands to explicitly invoke ABB commands, and the other reason this direction doesn't introduce any intrusive changes into U-boot, particularly bootcamp implementation. So here we have some subset of ABB commands which initialize ABB libraries, invokes this chain of trust verification process, and other commands just for debugging in case if we want to enable this feature for other boards and for debugging purposes. And the other feature, so ABB includes the process of verification of these partitions, and also it should supply a proper SIMD line to Linux kernel. So in this case we have to introduce additional params like what was device state, what was, if it was logged or not, AVB version, also some details about hash trees and what algorithms were used to verify partitions. So also we can perform some substitution of existing params like Android system partition, identification number, also boot partition, in BB meta partition, unique ID. It is example of how actually we invoke Android verified boot as verification. So here there are two examples of tempering partitions. So in first one I tempered boot or system vendor partition. So in this case, when we run AVB verification, we receive an error. Hash of data doesn't match digest in descriptor. And second one, as I already told before, that there is the way of verification of VB meta partition itself. So we also can temper VB meta partition and check that verification also fails. As we are using U-boot shell to invoke verification, the best way to run this verification is just change shell commands which boots Android. So in this case we introduce new additional environment, the additional variable in the U-boot environment, AVB verify. So basically there is a simple check. So we run this AVB verify. If verification is okay, we just append this AVB boot args that was generated from this boot args to the general CMD line. And in case if not, we just exit. So in this case, we don't continue our boot. And how it look like for some, for example, specific shell commands which boots Android. So in this case, we run this AVB verification mechanism before reading any FDTs, RAM disks, and so on. And only after we boot Android. Regarding this VB meta partition, the best way, frankly speaking, I started from using AVB tool, which actually is used for generating this VB meta structure. But there is a more convenient way. It's you can just enable in IOSP build system, just adding this 3 build flags. So basically, we board AVB enable. It enables AVB to support in Android. We specify which algorithm should be used, and specify the size of boot image. I've checked where boot image partition size is used, but it's only for the case when this VB meta structure is integrated into boot image. But it's not possible to generate VB meta if you don't specify this third build flag. Currently, all this what I've described, I have passed our internal review in Texas Instruments, and also we had a discussion with Tom Reilly, maintainer of U-boot. So currently, I'm addressing some of his comments and going to send all this what I have described before to the U-boot mailing list. So if you have any comments, please go on, and leave your reviews on patches. In the second part, major part, as I told before, there are three callbacks left, which should be implemented, but by Android verified boot README, it is recommended to use tamper evidence storage. So the best solution is to use RPMB partitions on eMMC. But the main problem about RPMB is that if we are the most easy solution is to leverage RPMB's driver in U-boot, but the main problem is that our private key is going to be stored in some normal vault, and it's possible that it will be disclosed. So as a solution, there is a secure storage implementation in Opti, and why not to leverage this feature? The main problem about communication from U-boot with T, specifically Opti, is some implementation of Opti client and Opti supplicant into U-boot. As currently we have only in Linux user libraries. So in this case we have to introduce two additional components into U-boot and secure storage trusted application, which is going to be an arbiter for each invocation of read rollback index, write rollback index, and get device log state. And in this case, secure vault is going to be used for building RPMB frames. So how it will look like? So from libAVB layer, we are going to use Opti client and communicate with secure storage, like call this get rollback index. Secure storage TA will decide if we have permissions or not, and then we'll use global platform core API for persistence objects, and we'll call read object data from Opti core, and Opti core RPMB file system component, and with leverage of FS key manager is going to generate RPMB frame and return it back to normal vault. And then we with the help of Opti supplicant and eMMC driver, we are going to communicate with eMMC controller and provide this generated RPMB frame from secure vault.
Quick question.
Yeah.
So in that case, secure don't really directly access the eMMC.
Right.
Okay.
So the major part of this work is to implement Opti portable client library. So this idea is based on the same similar stuff in AUSP, which is called keyless trusty IPC. So they have the same library to communicate with trusty TD, and it is supposed to be used from bootloader environments, and it is supposed to be ported the same way as libAVB and libAVB-AB. So we decided to follow the same way, but in the same case, provide some global platform T client API to U-boot. Also, the second major part is implementation of T supplicant, which is going to leverage eMMC driver from U-boot. It's a bit obvious slide because their major requirement is opt should be booted before U-boot, or it should be booted before Android verified boot will be involved. So some platforms, for example on TI, the way of loading opt works a bit different way than on other platforms. U-boot has a mechanism which leverage SMC calling convention to communicate with proprietary secure monitor, and so in this case we extract opt binary from feed image. We call secure monitor. We load it to RAM, and we call secure monitor using SMC calling convention to boot opt. So the problem is, currently we are thinking about how to change the way of booting. Maybe opt block will be packed into U-boot feed image. So basically, in this case, U-boot is it's not U-boot binary; it's a U-boot feed image. So it also can contain some U-boot blocks, U-boot device trees, and also we can put their T bin. So what is next? So finish implementation of functions that work with the rollback indexes. So in this case, opt portable client library will be implemented, and T supplicant to for access for use an eMMC controller driver from U-boot. Also, there is another major feature. It's AB slots. So when we have a set of it's the same partitions, and we decide which partition, which set of partition we want to use for current boot. So it is used for AB system updates, and it's just the way of seamless updates in Android. And integrate some AVB debugging capabilities into fastboot. It's read, write, rollback indexes, and lock unlock bootloader. And here's some references to this specific README, which explains what is AVB2 in details, and opt RPMB secure storage implementation and opt. Thank you. Any questions?
For the verification part, why do you just use the fitness verification mechanism? Because U-boot just supports some verification in feed image format.
Yeah, it has. First of all, AVB it's a requirement from Google. So for Android O, it's kind of recommended. For Android P, it's going to be mandatory feature.
Okay. And all these formats are defined by Google, right?
Right. So Google provides the way and specification how it should be implemented, and we should, but they doesn't stick to some specific bootloader. So that's the main problem.
Okay.
just out of curiosity, you were mentioning the Opti libraries, trying to make it so it's kind of bootloader agnostic. Are you actually collaborating with anyone else to kind of validate that?
Opti library, right?
Yeah.
I just started working on it, so
Okay.
basically I've focused on this part.
Do you have any plans, I guess, to collaborate with anyone else on a different type of bootloaders?
Yeah, if someone is going to help me, so why not?
Okay.
On the same question or similar question, Google is promoting Trusty. Does this framework work with Trusty? The one you're proposing here?
Actually, we are focused on Opti usage, so I guess I didn't actually follow this direction because.
Okay, so you're not sure if someone uses Trusty whether they could store the key in Trusty.
There is Intel bootloader. I don't remember I don't remember what it's called, but they have already support out of the box. So they've integrated this QMS Trusty IPC and libabb. So at least it's they have some reference implementation of communication from bootloader.
And the second question is, earlier you were implying there was a booting order issue. The secure word today is loaded by U-boot, right? So you have a kind of chicken and egg order problem.
Right.
Do you know, my memory is a little bit vague. With the ARM trusted firmware?
Yeah, it's.
This is not ARM trusted firmware,
Yeah, it's.
correct, right?
It's specific TI. Just a second.
Yeah. So
It's ARM v7. Yeah. So it doesn't. It has nothing in common with ARM v8, as we had a
Okay.
bit different boots.
So with trusted ARM, with the ARM trusted firmware, I forgot who boots the secure site.
It'll be booted with work, it's called.
I don't have this slide. So basically, we have ARM trusted firmware that boots up some secure payload, and only then we normal bootloader is booted. So in this case, we don't have this problem.
We don't have this
Yeah,
problem,
yeah,
right?
right,
Okay, I
right.
just want to confirm. It seems to be what I remember.
Go.
I just want to comment, I mean, one part of this work was also to add the support in U-boot. I mean, that's the big thing here. You were asking about if it's supported by Trust already, but there is no support for this in U-boot upstream today. So that's one big thing we're doing this.
Okay.
So.
Yeah, there's one question. During the steps, there is one steps. Basically, you have to figure out which partition is for the system, for example.
Mhm.
So my question was, is counter solution kind of agnostic to whether GPT is used or EBI is used? Basically, do you really care about how the partitioning scheme is actually being used?
Actually, currently it's only for GPT.
in GPT?
Yeah.
Yeah, because I think there's something kind of is missing in the U-boot. It's not only for verified boot, but also based the normal boot as well. So you have to specify what kind of
Mm-hmm.
partition scheme is used. Another question is, what is the TIN 257? Is ARM64 or 22?
It's based on Cortex A15, so it's on the 7. Yeah.
57, okay, yeah. That's because there's problem regarding, I saw you using boot N here, and for 64 bits, I think people usually use boot I, and there was a bit discussion on the U-boot as well regarding what is kind of proper way of booting an image.
Yeah, but the main idea, that's why I didn't stick to some specific way of booting, so this boot command. So in this case we have just two dedicated, dedicated command.
And another thing is when you even use boot I, you have to specify those addresses. That's actually part of the kernel RAM disk and the PTB address. So if we looking for have a kind of common or generic solution of booting Android, we have to solve this part as well, because for Android image it's not packed like the provide you those three address. For bootloader, directly you have to do a little bit of calculation because, for example, the BTB can be anywhere. So you have to do a little bit of working here.
bootm currently in mainline U-boot, it supports from Android image. So
Yeah.
actually it parses just and finds this magic symbol of Android image. So now then it knows how to boot it.
Yeah,
So-
but the Android image doesn't care or doesn't specify where you can put the DTB. You can
Yeah,
cut
right.
it at the end of the kernel. You can have a specific partition for it. So it is kind of back to the first question. There's no generic way to know where the DTB is, so you can provide this information to the bootloader to load all those information needed.
Right.
So,
Do you just verify the kernel, the DTB, and the RAM address, or you want to verify whole partition?
Yeah,
Whole partition.
there was the same question from Etienne, I guess, about verifying of DTB. Just a second. So, I've digged into libABB sources. So basically, we can use the same raw hashing verification of other partitions.
if the DTB is in the boot image, you just need to verify the boot
Yeah,
image.
yeah, right.
If the DTB is in another partition, you need to verify
Right.
another
right,
partition as
right,
well.
Right.
But that's kind of missing. I'm not sure if that because if you look at the recommendation, there's no DTB for.
I haven't checked it by myself. So the main problem, I didn't explicitly add this information. So I'm going to add also. We have a separate on TI source. We have a separate environment partition called environments. So I will just check it if it works or not. So basically, maybe I will introduce some changes into libABB to add support to this. But as we don't have any, theoretically we have some limitation of DB meta image, but we can also add some crypto descriptors for just a bunch amount of partitions. So I don't see any theoretical limitations with it.
How do you validate the U-boot scripts?
U-boot scripts. Just a second. As I said before, it's out of scope in this case. So, for example, if U-boot environment is a part of, for example, this block image, right? Or it should be verified by some specific verification way of which is basically defined by vendor. So in this case, we verify everything up to U-boot vendor implementation of verifier. So it's boot ROM verifies everything up to U-boot. So for example, on TI socks, we use some secure monitor, and we have a specific call like verify blob, and it consumes SPL and U-boot in this case. So for AVB, it's just out of scope.
I think for the currently, if I understand correctly, the procedure is you do the verify before you do the booting, right? You do verify and then the boot end.
Yeah,
It seems
right.
like, I'm not sure, maybe ideally we have to integrate this verification into the boot end in the code instead of having it in the script. I understand having scripts is more easy for you to verify those stuff, but it seems like if we integrate the verification in code-wise into the boot procedure, we don't need to worry about we have a missing piece of U-boot script that haven't been verified.
Yeah, but definition of boot something from memory. These callbacks is
Yeah,
working
yeah.
with working with
Yes,
eMMC
agree.
subsystem.
Yes,
So
agree. Yes. Somehow we have to do verification first and then
Yeah,
we do
right.
boot end. You don't need to.
Just so I understand, the library that you were building, it actually has to have the ability to make an SMC call into U-boot?
Right, right. And some stack wrapping this SMC call to make a proper call to Opti.
Yeah.
So it's
And does that mean you're actually gonna add like a global platform API for
Yeah.
secure storage
right,
to that library?
right. We're going to do this, but we still haven't some intermediate results. There are some examples of making secure calls in U-boot currently in mainline, so you can check TI specific code which communicates with this secure monitor. But it's just simple wrapper over SMC calling conventions. This is it. So they have some proprietary implementation of secure monitor, and just for two things, for installing Opti, or another secure payload, or verifying blocks like SPL and U-boot. So, how it looks like. So, in this case, boot ROM registers its own vector table in MD bar. Yeah, and we have the way it verifies first SPL, then SPL to verify U-boot next binary. It calls this boot ROM, which actually now is acting like secure monitor, and asks to verify U-boot. Then U-boot, currently in this implementation, does the same for feed image for every image in feed image. What I'm changing now, I introduce in the generic way of verification and verified boot, and in this case we are not going to use capabilities of secure monitor for verification everything after U-boot. We can discuss it after.
Yeah. It's a lot simpler in VA, I guess.
Well, it's just a slide for explaining some limitations of specific platform. Yeah.
Thank you.
Thank you. Yeah.